Okay, in this video we're going to talk about how to change a basis, meaning how to change vectors from being represented in one basis to being written in terms of a second basis. In order to do that, we're going to need to write everything in terms of matrices. We're going to use coordinate vectors to help us. So define a matrix B whose columns are the vectors in basis B. So if B is a basis for Rn, they're already going to be vectors, and so you just write them as columns and you're done. If B is a set of if our vector space is a set of polynomials or a set of matrices, then we'll have to find the coordinate vectors of those basis vectors in order to write them as columns of a matrix. So basically, whatever your vectors in B look like, write them as columns. Okay, so now I'm going to write a theorem down. It's a big theorem. The book describes this a slightly different way, but this is how I'm going to describe it. So if we have two matrices that represent two different bases, and we row reduce it, but in reduced row echelon form, it turns out anything that's a matrix corresponding to a basis, you're going to be able to get it to reduce down to an identity matrix. And this matrix on the right is actually going to be exactly what we need to change a vector from one basis to another. It's called a transition matrix. So we take two bases, we row reduce their corresponding matrices. The entry on the right side should be our transition matrix. And one thing that we do have to be careful of, the reason I'm writing instead of just as P, which is how the book writes it, I'm writing P with two little b's, is it's really easy to get mixed up which basis are you leaving and which basis are you entering. So I'm always going to write two of them, and then we are going to have to figure out which one is it going from and which one is it going to. If I write it this way, P times a vector, I know that when I look at size of a matrix, I want the inside dimensions to line up, and we're basically kind of mimicking that notation where we want these to both be in the same basis. So if V is written in terms of a B basis, we want the transition matrix that has the B on the right, which means this B is on the right. And then if B prime is on the left, that's what our answer is going to be written as, is a vector, a coordinate vector relative to B prime. Okay, so that's a little confusing. That's a lot of stuff jammed into one theorem. Let's look at a particular example. So I have two bases for the set of polynomials of degree 1 or less, and I'd like to find their corresponding matrices. So let's see. I'm going to think about this relative to the standard basis, which would be x comma 1, and relative to the standard basis, this is the vector 1, 1. Its coordinates are 1 and 1. The coordinates of this are 2 and negative 1. So I'm writing those as columns. I don't really need that bar. I'm just putting in there so you can see they're coming from columns. And B prime, same thing over here. We have x plus 2, which would be coefficients 1 and 2. And 3x plus 5, which would be coefficients 3 and 5. Again, relative to the standard basis, those would be our coordinates. Okay, so in order to find a transition matrix, I just have to put B and B prime next to each other. Let's see, I do have to be careful which one am I leaving, which one am I entering. So it says from B to B prime. The one that says from is on the right. So from B means B is on the right. So our transition matrix, we're going to need to put B prime on the left and B on the right. So the order is really, really important. Okay, so B prime B is going to be 1, 2, 3, 5. And this is an augmented matrix with B on the right, 1, 2, 1, negative 1. And then I'm going to find the reduced row echelon form of that. And I'm just going to type that in a calculator. It turns out the answer you get is 1, 0, negative 2, negative 13, 0, 1, 1, 5. So supposedly the transition matrix P, which I'm going to write as P with B on the left and B prime on the B on the right, B prime on the left. So same order on the left side as you see on the subscripts of P, is going to be this matrix on the right side, negative 2, negative 13, 1, 5. Okay, So suppose I got through that far just by plugging and chugging. How do I make sure that I did this right and I didn't get the b's mixed up? So let's check our answer. So in order to check our answer, we have to find the same vector in two different bases. Check and make sure that a particular vector relative to b, how does it compare to that same vector relative to b prime? And since we're having a transition matrix that leaves b and enters b prime, I think I would rather find a vector that starts in b. So let's see, my favorite vector in b, I'm just going to pick x plus 1. It seems like it's going to be a simple vector relative to b. And so our coordinates relative to b, you don't really need to solve for the coefficients relative to b. If this is a multiple of x plus 1 plus a multiple of this other guy, well, it's got to be 1 times x plus 1 and 0 times 2x minus 1. So our coordinate vector is just going to be 1, 0. If you don't believe me there, you might want to double check and run through the previous video how to find the coordinate vector of a particular vector relative to a basis. Okay, so supposedly according to our theorem, v relative to b prime should be this p from b to b prime times vb. So let's multiply those out. -2, -13, 1, 5 is our p. vb is 1, 0. And if I multiply those two, first row, first column gives us -2. Second row, first column gives us 1. So supposedly this is our coordinate vector of the same vector v relative to b prime. So let's check it out. Is this actually correct? So if this is right, then v should be equal to -2 times the first vector plus 1 times the second vector. Remember, a coordinate vector is really just what are the constants in the linear combination. And I'm just going to slide up slightly and put a new piece of paper. Okay, so our last line was v question mark -2x plus 2 plus 1 3x plus 5. Okay, let's distribute and check it out. We have -2x minus 4 plus 3x plus 5. Combine like terms, 3x minus 2x is 1x, and -4 plus 5 would be 1. Is it true that v is 1? Or sorry, v is x plus 1? Yes. That looks right. So we started off with v having coordinate vector 1, 0 relative to the b basis and having coordinate vector -2, 1 relative to the b prime basis. The relationship between these two is given by this particular p. And one last little thing I should mention. This may or may not be obvious. If you get the two b's in the wrong place, what you're actually going to do is find the inverse transformation. The inverse of this matrix is this matrix. Okay, and the idea being if you can transition from b basis to b prime basis by multiplying by this p, you should be able to transition back by using its inverse or multiplying by its inverse.